So this is the fourth lecture of this course and the second lecture on the topic equilibrium carrier concentration. Let us recapitulate what we did in the last class. In the last class we mentioned that we are considering the carrier concentration in the bulk region of a semiconductor under equilibrium conditions. We mentioned what is meant by equilibrium or thermal equilibrium conditions, and we distinguished thermal equilibrium from steady state. So these are the ideas we considered yesterday. We also saw some of the variations of the concentrations of electrons and holes in semiconductors, in pure semiconductor and in doped semiconductors. Also we distinguished between pure and intrinsic semiconductors. We also saw what is the difference between simple or elemental semiconductors and compound semiconductors. Today we will proceed further, and to begin with we will consider the topic of wave particle duality. The important principle or the important concept of wave particle duality, what does it mean? It says that the energy or matter propagates in the form of streams of particles or as travelling waves. So energy or matter travels, you can regard the energy or matter when it is propagating as propagating either as streams of particles or as travelling waves. Let us look at some of the travelling waves, how they are generated and so on. Now here I would like to also show you in this context how internet can be used as a very good reference material for understanding a subject. In this particular context it is semiconductor devices. So for instance, a large number of animations of various ideas and concepts are available on the internet. Let me show you some of the animations related to the waves. So all that I do is I go to internet and do a Google search. So for example, in this case, let me do it live in front of you. So I can put waves here, and then I could add another word, maybe animation or applets. And then I will get a number of options. Now here I could pick from here any one and then see what is there. Okay. So I have picked some which I am going to show you. Okay, let's look at this electromagnetic waves. I am playing this applet with the permission of the people who have developed it. So although this is talking about electromagnetic waves, you can also understand how, for example, elastic waves are generated in ropes. So imagine that this is like a rope, this green line is like a rope, and then one end is flexed, okay, and then released. So what you have is a travelling wave generated from that end. So you are constantly flexing one end of the rope periodically, and what is emanating from there is a travelling wave. So that is the kind of waves we are talking about. Okay. Let us look at some of the other waves. This is here we have two examples, one of a stationary transverse wave and other a longitudinal wave. So let us look at the stationary transverse wave. So what is this? This is an example of a travelling wave generated from one end and another travelling wave generated from the other end, and the two interfering so as to give rise to a standing wave. Okay, so this is a standing wave pattern. So it is a travelling, it is an interference of two travelling waves. The standing wave is a consequence of two travelling waves. So when do you say a wave is travelling? When some quantity of the wave is varying both as a function of space and as a function of time. So which means at any point in space, if I look at that parameter of the wave, it will be varying as a function of time. Or at any instant of time, if I look at the wave in the space, that parameter will vary with distance. Okay, that is what is a travelling wave. Let's look at another travelling wave. If you drop stone in water, okay, this is how you will have ripples generated. So this is another travelling wave. This is an elastic wave because it is a wave generated in a medium wherein atoms are displaced with respect to time and distance. Now you can have interference of such circular waves. So you have a circular wave emanating from one point, and then it is going and hitting a surface from where a reflection is taking place. In other words, another wave is generated and the two interfere. Okay. So these are some of the examples of travelling waves, and this will give you a feel of how parameters of the wave vary with distance as well as time. This visualization of the wave is important to understand further what is the idea of wave particle duality. Now let us look at some of the examples of wave particle duality. Now in this table I have listed here streams of particles such as photons, electrons and phonons. You are familiar with photons and electrons, you may not be so familiar with phonons, so we will discuss about them. Now photon is a particle, its equivalent wave, travelling wave, is an electromagnetic wave. You can take down as I am describing. So I will be going slow so that you can take down. Now what is it that varies for an electromagnetic wave with distance and time? So it is electric field and magnetic field. These are the two parameters which vary with x and t. What are the equations that describe this wave? These equations are named after Maxwell, the Maxwell's equations. Similarly, you can take the electron, streams of electrons. The travelling wave that is associated with the electrons is the de Broglie wave. So de Broglie was a scientist who showed that matter can also travel as waves. Now in a de Broglie wave, what is it that is varying with time and distance? It is a probability. It is a probability wave. So probability varies with distance as well as with time, and the equation governing this particular wave was given by Schrödinger, the Schrödinger's equation. As against this, let us take the phonons. I will come to the particle aspect of phonon a little later. Let us start with the wave aspect of this particular particle, that is the elastic wave. We have just now seen some elastic waves, say the travelling wave in a rope or the ripples in water when a stone drops on the surface. These are all examples of elastic waves. Okay. Now here, what is it that is varying with distance and time? It is the atomic displacement that varies with distance and time. The particle equivalent of this wave is called the phonon. Why is it called the phonon? So the name phonon comes from, is related to sound. So when sound is travelling in solid, it is an elastic wave that is created. in the solid. And the particle equivalent of sound, phono stands for sound. So a particle equivalent of that is phonon. So although strictly speaking it is associated with propagation of sound in a solid medium, in general it is used as a particle equivalent of an elastic wave, okay, that may be generated in any solid. Now there is because there are a number of elastic waves, you cannot associate any single scientist with this elastic wave. That is why this particular column in this table, slot in the table, is left blank. It does not mean that there is no equation, it only means that there is no single scientist or single equation that you can identify with this particular form of wave particle duality. Now let us understand what is the advantage of using this concept, because any concept is introduced to simplify the understanding of some situation. Let us try to see the equations which relate the particle and wave aspects. For example, you know the equations: E, that is energy, is equal to Planck's constant h into frequency of the wave. Another parameter is P, the momentum, which is related to the wave aspect as h by lambda. Here E and P, these two parameters represent the properties of particles in the stream. On the other hand, these parameters, namely nu and lambda, represent the particle of properties of waves associated with the streams of particles. Note that as the word travelling in the phrase travelling wave indicates, the wave involves a propagation. So here, for example, nu is a parameter representing variation with respect to time. On the other hand, lambda, the wavelength, is a parameter that is related to variation with respect to distance. This energy E and P written here in these equations also represents the energy E and the momentum P written in these equations also represents the minimum energy, the minimum quantum of energy that can propagate. Minimum, not exactly energy, because E is energy, so what we will do is we will keep P in brackets. So E represents minimum energy and P represents momentum. Quantum that can propagate. So as you know, the important thing in quantum mechanics is things don't vary continuously, they vary in discrete sizes. okay, discrete amount. So what is the minimum amount there involved in this variation? This is the amount, E or P, as given by the equation E equal to h into nu and P equal to h by lambda. Let us consider an example to see what kind of wavelengths are associated with energies. Okay. So for example, let us take the energy of 1 electron volt. One electron volt represents the energy that is gained by a unit charge, okay, of value 1.6 into 10 power minus 19 coulombs when it falls through 1 volt. So if you want to write this energy in joules, it would be 1.6 into 10 to the power minus 19 joules. Let us assume that we are talking of an electromagnetic wave. So in electromagnetic wave, if energy is 1 electron volt, what is the wavelength? So now we use the equation E is equal to P is equal to h by lambda. So lambda is equal to h by P. Now how do you know P? So there you have the other equation, E is equal to h nu. The wave speed is given by, wave speed is v, that is equal to mu into lambda. Okay, so we combine these equations. So how do you combine these equations? You can write, instead of using lambda is equal to h by P, let us proceed as follows. Let us express P in terms of E and V. So we can write P by E, the h will get cancelled, is equal to 1 by nu into lambda, that is equal to 1 by wave speed V. So P is equal to E into E divided by the wave speed. And now we can write lambda is equal to h by P, which is equal to h into V upon E. So lambda is equal to h into V upon E. Next, let us substitute the values. So the wavelength lambda corresponding to 1 electron volt is equal to hV by E, which is 6.626 into 10 power minus 34 joule second. Note that I am putting the numerical value as well as the units. This is important whenever you make a calculation of a physical quantity in terms of other physical quantities, you must put the values as well as the units of all the quantities. Otherwise you are not sure whether you are using the right units and your numerical value is correct. Now v is the velocity of light, that is 3 into 10 power 8 meters per second. Now this is where I want to again emphasize the importance of units. we might remember the velocity of light in terms of centimeter per second instead of meter per second. If I were to put this unit in centimeters per second, that is 3 into 10 power 10 centimeters per second, then my numerical value that I will get will be different, and that would actually not be correct, because joule seconds is an MKS system, whereas centimeters is not the correct length unit for MKS system, it should be meters. So that is why we must write the velocity of light in meters per second when we are writing the Planck's constant in joule seconds or MKS system. Now the energy E, 1 electron volt is 1.6 into 10 to power minus 19 joules. So I put the joules here. Now first thing is we must check the units. So this joule cancels with this joule, second cancels with second, and you are left with meters. So my value that I get here will be in meters. So the result is 1.24 into 10 power minus 6 meters, which is same as 1.24 micrometers. Next, let us look at the specific advantages to be gained from this idea in the context of semiconductors which we are studying. For example, if you want to know what is the effect of light falling on the semiconductor, this is equivalent to an electromagnetic wave falling on the semiconductor. Now this interaction between an electromagnetic wave and the semiconductor crystal or semiconductor atom can be represented by assuming the particle equivalent of the electromagnetic wave. And in fact, if you recall, in the first lecture we showed generation of electron hole pairs from an electromagnetic wave or a photon. So we showed something like this. Okay, so this is a photon or a stream of photons falling on the semiconductor crystal, falling on a semiconductor atom in this case, and then you have an electron hole pair generated. Now this particular phenomenon can be regarded as a collision of a photon with an atom in the particle equivalent parlance. Okay, so instead of regarding as a wave interacting with an atom where the things look more complicated, if the wave is converted into its particle stream, regarded as a particle stream, then it becomes a simple problem in collision. So it is a collision between a photon and an atom. And so now you can treat this collision from the energy momentum conservation point of view and find out whether the photon, can it generate an electron hole pair. You have to find out whether it can break the bond, whether it can supply the energy that is required to make an electron free. Does it have a momentum? Okay, and so on. And this way you can treat this particular interaction. Take another example. When you have a semiconductor crystal at T greater than 0 K, at T greater than 0 K, you know the atoms are in agitation, and each agitating atom gives rise to a travelling wave. In detail we will discuss this later. Now you can take it as a fact that each vibrating atom, because this atom is bonded to the next atom and the next atom is bonded to the next atom, the series of atoms which are bonded together can be regarded as a kind of continuous solid medium, as an analogy. And therefore if any one atom vibrates, since it is bonded to other atoms, the other atoms also are set into vibration, and what is generated is a travelling wave. So in a semiconductor for T greater than 0 K, you have atoms agitating and giving rise to travelling waves in which atoms are displaced as a function of time and distance. Now what is the effect of these elastic waves? These travelling waves are elastic waves. What is the effect of these atomic vibrations or these elastic waves because of the atomic vibrations on electrons? If you want to know, it is a rather complicated picture when you look at it this way. But now if you regard the elastic waves as streams of particles called phonons, this becomes a collision between phonons and electrons. So now you can regard this collision between phonons and electrons, we can treat this collision from the energy momentum conservation point of view, okay, and then we can see how this collision affects, for example, the mobility of electrons. How is it that travelling waves, elastic waves present in semiconductor solid, how do they affect the movement of electrons? This can be easily treated as collision between phonons and electrons. So in all these collisions between particles, we assume the energy and momentum conservation laws, okay, and treat these collisions. Now we have discussed the basic concepts, namely the thermal equilibrium, steady state, and then wave particle duality. Now with these ideas, now we can proceed to see in detail what is happening within a semiconductor and how do you get the electrons and holes, okay. So now we will start with what is called the bond model of a intrinsic semiconductor. So first we take up the intrinsic semiconductor and then we will go to the extrinsic semiconductor, which is the more complicated semiconductor. Now here when I use the word intrinsic, for our discussion we will be considering a pure semiconductor without any defects or impurities. That is what we are going to assume, that is the model we are going to develop is for such a semiconductor. Now in any such modeling you must understand there is an important approach, and that is first you discuss the model in a qualitative fashion and then only you write the equations corresponding to the model phenomena. In other words, you must always discuss the qualitative theory first and then the quantitative aspect. This qualitative theory is very, very important because this is what gives you the insight, this is what tells you whether you have understood what is happening within the semiconductor. So one must not think that when you say a model it is the equation. This is not correct. The word model actually includes the qualitative understanding and later on its translation into an equation. So let us first discuss this model of a intrinsic semiconductor in a qualitative fashion, that is the so called bond model. As we will see, a quantitative model of this semiconductor is the energy band model. So this model will not help you to make accurate calculations of concentration of electrons or holes as a function of temperature. But what it will help you to do is, one, it will show you why there are electrons and holes. Why is it that you have electrons, negatively charged particles which can carry current, and holes, positively charged particles which can carry current in a semiconductor, and why such things are not there in a metal. It can also explain to you why is it that the temperature coefficient of resistivity of semiconductors is negative. That is, when the temperature increases in some range, the resistivity falls. In other words, it will explain why the concentration of carriers should increase with temperature in an intrinsic semiconductor. Then it can also give you a rough idea of the concentration of the semiconductors, a rough idea of the concentration, what kind of orders of magnitude are involved. The first step in this model is to look at the crystal structure. You know that any crystal has regular arrangement of atoms. It involves repetition of what is called a unit cell or a unit cube. Let us draw the unit cube of silicon. the length A of this cube is normally called the lattice constant. Where are the atoms located in a unit cube of silicon? So you have one atom at each of the 8 corners. One atom at each of the 8 corners. So 8 corners are 1, 2, 3, 4, 5, 6, 7 and 8. They are the 8 corners. Then you have one atom on center of each of the 6 faces. So atoms at 6 face centers. And then you have 4 atoms located near 4 corners, which I will show which are the 4 corners. So it could be this corner and its opposite A and B, and then C and D on the top. So if the A and B are located at these 2 corners here at the bottom, then the C and D are located in such a way that this line CD, this diagonal CD, okay, is at 90 degrees to this diagonal AB, if you see from the top. So these are the 4 corners, A, B and CD. So atoms near, this is not exactly at, because we already said that there is an atom at each of these corners. So atoms near 4 corners A, B, C, D. Now we will consider what is meant by the exact location near this particular corner, right? So let us take the atom that is located near the corner A. It is at a distance A by from 4 in this direction, then A by 4 in the perpendicular direction here, and then A by 4 in the vertical direction. Okay, so this is the atom. This is A by 4, this is A by 4, and this distance is also A by 4. So A by 4, A by 4, A by 4, X, Y, Z in these directions from that corner. You can similarly locate atoms at corner B, atoms at corner C and D. C and D would be within the cube. So it would be A by 4 in this direction, A by 4 in this direction, and A by 4 down. Okay, I am not showing you all the atoms because then the picture may or may not be clear. In fact, I would urge you to take a look at the internet in this context. There are a number of applets and animations available of the crystal structure where you can rotate this particular unit cell and see how it looks from different angles. So the important thing that we need to know from here is that there are 6 atoms, there are 8 atoms at 8 corners, 6 atoms at each of the 6 face centers. For example, if you take this face, the atom will be located at center of this face here, and similarly there is one atom at each of the 6 face centers, and then there are 4 atoms within the cube located near the corners A, B, C and D. Now what is important to note is that each atom in this particular arrangement is bonded to 4 neighboring atoms. So let me show you this with the help of this particular atom, to which 4 nearest neighbors is this bonded. So this atom is bonded to this corner. It is also bonded to the face center of this face. So that is here. Then it is bonded to the face center of the bottom face. And it is bonded to the face center of this side face. Now like this, the atom at the corner B will also be bonded to the 4 neighboring atoms. Atom at corner C and atom at corner D will also be bonded, and if you see all the bonds, you repeat this arrangement, and if you see the various bonds and the arrangement of atoms, what emerges is that it is a regular arrangement in which each silicon atom is bonded to 4 neighbors. Since it is difficult to work with this 3-dimensional arrangement, and in practice what is of interest to us are these 2 aspects, that is a regular arrangement of atoms and each atom bonded to 4 neighbors, we can always use a 2-dimensional representation of the 3-dimensional arrangement for purposes of understanding. So that 2-dimensional arrangement would be as follows. So this is like a matrix or a network wherein each intersection between 2 lines indicates an atom, presence of an atom, and each line between the 2 such intersections, so let us say this line, it represents the bond between the 2 atoms. So you can see in this arrangement every atom is bonded to 4 neighbors. So it just so happens that for silicon every atom is bonded to 4 neighbors, and we can conveniently use a 2-dimensional representation, okay, showing this particular arrangement. So for example, here if I take this atom, its 4 nearest neighbors would be this, this, this and this, and these are the bonds. For this atom the 4 nearest neighbors are this, this, this and this, and so on. So this is a 2-dimensional arrangement or representation of a 3-dimensional crystal. Now let us look at some of the numbers associated with the crystal structure. So here on this slide we have shown some parameters that you must know, some facts that you must know for silicon and gallium arsenide, which is a compound semiconductor. So let us take up these table quantities one by one. The group silicon is a group 4 element. So since it is a group 4 element, it has 4 valence electrons. We will first take the various parameters for silicon, and then we will go to gallium arsenide. So atomic number of silicon is 14, so it has 14 electrons surrounding the nucleus, out of which 4 are the electrons in the outermost orbit, they are the valence electrons because they participate in bonding. Then comes a very important number, atomic concentration. What is the concentration of atoms in a silicon crystal? So the concentration is 5 into 10 power 22, unit is per centimeter cube. The crystal structure of silicon is called diamond. It is also called the tetrahedral structure. The lattice constant, that is the length of the unit cube, which is this particular parameter A, this length of the unit cube. This constant, the value is 5.43 angstroms. You must become familiar with units associated with very small dimensions. Okay? So one unit that we came across was micron. Many of the device sizes are in microns. Okay? Now how do you remember, how do you have a feel for this dimension? See, for example, if you are asked to tell the dimensions of this room, you are probably likely to tell the dimensions in meters or feet, and just by looking at the room one can get a feel. You can, for example, look at the blackboard and say what are the dimensions. You can tell the dimensions in feet or meters. Now if you want to have a feel for a micron, how do you get a feel for micron? So as I mentioned once earlier, our hair is 50 microns thick. Okay, human hair is about 50 microns thick. So 1 micron is 1/50th of that thickness. Okay. Now you must know similarly an angstrom. Okay. So it is easier to remember an angstrom in terms of microns. So what is the dimension of an angstrom? 1 angstrom is equal to 10 power minus 10 meters, or if you want to remember in terms of centimeters, 10 power minus 8 centimeters. If you want to remember in terms of microns, it is 10 power minus 4 microns. In other words, 1 micron is equal to 10,000 angstroms. So in terms of this dimension, the lattice constant is 5.43 angstroms. And then finally you have the bond energy. On this slide you have the bond energy, that is 1.12 electron volts for silicon. So the energy is represented in terms of electron volts. Is there energy required to break the bond between two silicon atoms, covalent bond. The analogous values of the various parameters are given here for gallium arsenide. So gallium is group 3, arsenic is group 5. So gallium arsenide is 3,5 semiconductor. I leave it as an exercise to you to find out other 3,5 semiconductors. Then you cannot talk of an atomic number here as such. Atomic concentration 4.42 into 10 power 22 per centimeter cube. So you can see the atomic concentrations in various materials are somewhat similar. The order is 10 power 22. This is very important to remember, that the order of concentration of atoms in solids is around 10 power 22. The name of the crystal structure for gallium arsenide is zinc blende. Then you have the lattice constant 5.65 angstroms, and bond energy is 1.42 electron volts. So now the next step would be to look at how electrons and holes are created when you raise the temperature of a semiconductor beyond T equal to 0 K. As we have said, we will always consider silicon as an example unless stated otherwise. So silicon crystal for T greater than 0 K. Now let us start with the picture for T equal to 0 K. T equal to 0 K, there is no thermal agitation, and so your picture is something like this. There is no agitation, all the atoms are bonded to 4 nearest neighbors, no bond is broken. Okay, so it is something like this. Now when you raise the temperature beyond 0 K, what happens is that each atom starts vibrating about its mean position. And now whenever an atom vibrates, as we have said, it will generate an elastic wave. You can regard this picture as analogous to what happens in a pond when raindrops are falling. Supposing there is no rain, the top surface of the pond is calm. Okay? Now once the rain starts falling, wherever a raindrop falls, from there a ripple is generated, circular waves that we have seen. And now these ripples will emanate from each of the drops and they will interfere. Exactly similar thing happens here. From each of the atoms that is vibrating, a travelling wave is emanating and it is interfering with the travelling waves generated from the other atoms, emanating from the other atoms. So you have elastic waves within the crystal. Now looking at our wave particle analogy, we can therefore say that for T greater than 0 K, you have phonons moving about in the crystal. So there are elastic waves created, elastic waves of atoms created, which can be regarded as streams of phonons. So first set of particles that we get are the phonons. So at T greater than 0 K, you have phonons. Now we can show that you will also have photons. How do you show that you have photons? Photons are analogous to electromagnetic waves. How can we show that a vibrating atom in a silicon crystal is going to give rise to electromagnetic waves? This is very important to understand. Now this can be explained with the help of an animation. Now what is shown here on this slide is the positively charged nucleus, which is dark blue. This is a positively charged nucleus, and surrounding it is a negative electron cloud corresponding to the electrons. Okay? Now when an atom is vibrating, how does this charge picture look like? Charge picture looks something like this. So you have the electron cloud not moving along with the nucleus, it does not move along with the nucleus. Okay? There is a relative displacement between the center of the electron cloud and the positively charged nucleus. Now if you regard the center of the electron cloud as representing a negative point charge and the center of the nucleus as a point charge which is positive, then you can see that between the positive charge of the nucleus and the negative charge of the electron cloud, there is a dipole created because these two are displaced with respect to each other. So you can see the black dot here and the horizontal line of the black dot represents a negative charge, it is a negative sign, whereas the positive charge is shown here in the nucleus. So this relative displacement of the positive and the negative charges creates an oscillating dipole. So we can say a vibrating atom is an oscillating dipole. So when I say dipole, it is an electric dipole. Now you know that whenever there is an oscillating charge or oscillating dipole, as per Maxwell's equations, the charge must radiate an electromagnetic wave. So an oscillating dipole is the source of electromagnetic wave. This is a dipole, and if the distance between them is changing, the dipole oscillates, okay, something like this. And from this point, when the oscillations take place, an electromagnetic wave is radiated. So that is how every vibrating atom in the silicon crystal is also a source of electromagnetic wave. It is a source of elastic wave, that is phonons. It is also a source of travelling wave, that is electromagnetic waves. Therefore you have photons moving about in the crystal. So you have phonons, then you have photons. Now as we said, these waves emanating from different atoms will interfere, okay. In the particle equivalent parlance, we can say that many particles can converge onto a point. Waves interfering from waves emanating from different atoms interfering at a point is equivalent to many particles converging onto a point. And if this happens, if the total energy of these particles is more than the bond energy between two atoms, that is 1.1 electron volt in the case of silicon, then it is possible to break the bond. What is the consequence of breaking the bond? After all, a bond is created between two valence electrons, between two atoms. One of the electrons is being set free, okay. So when one of the electrons is set free, you have a free electron. So this is how a large number of particles converging on to a atom can give rise to a broken bond. In other words, it can give rise to a free electron. Electron jumps out of the bond. So this can be shown on this diagram as a broken bond, and an electron being set free. What is the meaning of electron being set free? It means that it is no more localized to any atom. It is not sufficiently free to be outside the crystal. It is only free of the particular atom which was holding it, but it must move about within the crystal. So it does not belong to any single atom. In that sense it is free. No atom can claim that it is mine, okay. So in that sense it is free, but it is free to move about only within the confines of a crystal. That is the free electron. So this is the so called free electron. And now there is a vacancy left behind by the free electrons. Since absence of a negative charge, the neutral region will be acting like a positively charged place, because with the electron everything was neutral. So in the absence of the electron, it has become positively charged. So there is a vacancy left behind, and that vacancy is called the hole. Since it is devoid of a negative charge and it is neutral with the electron or with the negative charge, the vacancy is positively charged, okay. So what we gather from this description is that for t greater than 0 k, within a semiconductor crystal, there will be 4 types of particles moving about. These 4 types of particles are phonons, which are elastic waves emanating from atoms; photons, which are electromagnetic waves emanating from atoms; free electrons, okay, which can also be regarded as de Broglie waves. Free electrons created because a large number of photons and phonons can converge onto a silicon atom, and if their total energy exceeds the bond energy, they can break a bond. So you have free electrons, and an electron that has left a vacancy. The vacancy itself, as we will see in detail later, it can move about, and it is positively charged, it can respond to electric fields, it can move in the response to electric field, therefore it can be treated as a carrier of current, and this is the hole. Okay, so electrons, holes, phonons and photons, they are the 4 types of particles which are present. We will discuss on this model later subsequently in the next lecture.